You're listening to Wurth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast. Today's podcast once again comes directly from a recent webinar presented by Wurth Electronics' own Frank Fraber. Frank is a Wurth Electronic application engineer, and in our latest presentation, he discusses the mechanical and electrical properties of low insertion force, or LIF connectors, zero insertion force, or ZIF connectors, and the flat flexible cable, known as FFC. We'll start by defining the characteristics and the differences of each connector, and then we'll explain how you can select a suitable component for your application. We'll also give examples of how the FFC cable can fit into an application, and based on impedance measurements, consider the losses at different frequency in single mode and differential mode. So sit back, relax, and enjoy today's Wurth Electronic What's Up podcast presentation, an in-depth look at the mechanical and electrical properties of ZIF, LIF, and FFC.
The agenda is divided into a mechanical and an electrical part. The mechanical part is definitions, what is behind the different terms, and product overview, overview of the pitch and properties of ZIF and LIF connectors, the different contact style, what contact options are there, different locking types, what types of locking are there and how do they differ. FFC, it's an overview and properties of FFC cables. Are there also other options beyond the standard? After this, we are talking about the electrical part. It's about impedance, display of the impedance behavior in the overall system, taking into account different grid dimensions and cable lengths. Basically, we have two different types of connectors in this range. These are ZIF, or zero insertion force connectors, and LIF, low insertion force or minimum force connectors. ZIF connectors always have an actuator. With the actuator, it is possible to lock and release the cable in the connector. With a LIF connector, on the other hand, the cable is held in place by the spring force of the contacts and can therefore be inserted and removed from the connector with a minimum force. The FFC is a flat flexible cable. We have this in different versions, more on that later. FPC is a printed circuit board with a flexible connection element. This can be inserted directly into the connector. All of our connectors from this area are only available as SMD variants. The orientation of the connector is either horizontal or vertical. And in addition to the standard types, we also offer low profile types, but only with our ZIF connectors, not with the LIF types. I'd like to show you our product in detail here. As we can see on this page, there are two different pitches in the ZIF category. These are the ZIF with 0.5 millimeters and the ZIF with a 1.0 millimeters. At this moment, we had the LIF connectors on this side only in the pitch of 1.0 millimeters. We hope that we can offer you the LIF types with a pitch of 0.5 millimeters in a few months. We had two different current specifications. You can see it here. The smaller currents are given for the low profile types. Some basic information on the number of poles. As a rule, these are always even numbers. There are a few exceptions with odd numbers. The main difference between ZIF 0.5 and 1.0 millimeters. They differ in the number of poles. You can see it here and here. With a pitch of 1.0 millimeters, there is no backlog available as an actuator. And the main difference between ZIF and LIF types, there is no low profile variant available here. So you can see a low profile here at the ZIF connector and here, but not on the LIF connector. As previously mentioned, there is no actuator on these types. The cable is held in place by the spring force of the contact. Here we see our available contact styles. We associate these with the various locking types, but more about this on the next slide. Let me explain how the contact works. The top contact, you can here see it on the left side, is only available with a slider as an actuator. This is the slider and these are the contacts. The explanation of the different actuators follows on the next slide. Here we want to devote ourselves to the type of contacts. The dual contact is only available with the backlog variant. You can see it on the right side. Because a contact cannot take place where the actuator is due to the mechanical structure. More on that later. To the difference between top, bottom, or dual contact. With the top and bottom, the contacts are only on one side. Here are the contacts, and on the other side is the actuator. And here, the bottom contact, the actuator is on the other side. With a dual contact, the contacts are on both sides. You can see it here. Therefore, it doesn't matter which type of cable it is used, type 1 or type 2. The dual contact variant is therefore only available as a horizontal system. Finally, the locking system is also a hinge type. Now, as promised, to the different types of locking. On the left, we can see a cut through a bottom contact connector here. We can see that the contact teeth here are on the opposite side of the latch, this one. In this case, a slider. The slider is valved. You can see it here. This enables us to route the cable at right angles when pressing it and at the same time make contact on the pronounced part of the slider here. The cable is thus pressed more and more strongly against the contact teeth when locking on this. In the picture in the middle, we can see how the slider is guided. You can see it here. This should facilitate a right-angled insertion of the cable and prevent the slider from jamming. In the picture on the right side, we can see same locking system in the top contact version. These are the top contacts. This picture shows a section through a vertical or an upright ZIF connector. Vertical connectors are only available with a slider as an actuator. You can see the slider here. Now you might be wondering if this is a top or a bottom contact. This definition does not exist for the vertical types. But how to determine on which side my cable contacts? With this type of connector, the contact is always on the opposite side of the slider. This is the slider and the contacts are on the opposite side. The backlog actuator is ultimately also a kind of hinge type. We will come to this hinge type in a moment. The difference between backlog and hinge type lies in the placement of the actuator. At the cable entry point, then it's on this side, or opposite it like this. Only the connector variant with backlog can be a dual contact variant. Why? Due to the mechanism just shown, there is only enough space for the mechanism in the backlog. You can see the mechanism here. Placing the mechanism on the side of the cable entry is not possible. Let's look at the mechanism in detail. Here we have a semicircle, you can see it here, that is vertical in the locked position, like this. And horizontal in the unlocked position. So the slider goes angled like this, and then it's horizontal. This pressed the cable against the contact teeth. You see it here. On this slide is our hinge type. The hinge type is always a bottom contact. You can see the contact teeth here. Let me briefly explain why this is so. The contact with the contact teeth is designed as a kind of spring contact. This is a spring contact. In the illustration, the connector is locked. The contact spring presses the cable onto the teeth here. The plastic clip is vertical. You can see it here. If you move the actuator upwards in a 90-degree movement like this, the contact spring is relieved and the cable can be removed. The plastic bracket then is horizontal. This is the plastic bracket and then it's horizontal like this. Due to this structure, a hinge type can only be available as a bottom contact. Otherwise, the actuator would have to be released downwards or towards the PCB. This is not possible. With this slide, we want to point out the difference in layout. The layout is almost the same for the locking style slider, top or bottom, as well as for dual contact. These types can therefore be interchanged easily. The hinge type is a special feature here. The layout is not 100% compatible. We see our hinge type shown in green, here, here, and here. Our other types in red. You can see it here and here. The pads of the contact pins are almost the same. You can see it in the top. But there are differences in the pads for fastening or holding the connector, as shown before. This affects both the 0.5 millimeter grid and the 1.0 millimeter grid. Please pay attention to this when selecting the connector. Each of these illustrations is a section through our LIF connector. As mentioned at the beginning, there is no actuator here, but the cable is held by the spring force of the contact. You can see it here. This has the advantage that the connector can be made smaller in items of its external dimensions and less space is required around the component to access the actuator. At the same time, the time for assembly is reduced since the cable only has to be plugged into the connector. Active locking is therefore no longer necessary. In the case of the vertical or standing variant, you can see it on the right side. The opposite lead of the contacts can be seen very nicely. You can see it here and here. This simplifies the positioning of the component on the circuit board. At the same time, we increase the mechanical stability. But how to recognize where my contact surface for this cable is? At the ZIF, we just talked about the reference point of the actuator and its opposite side. Here it is the case that the contact brackets, this one, are visible from the outside. from the top in this case. So you can orientate yourself on that. The LIF variant is currently only available for with a pitch of 1.0 millimeter. Pull-out forces are shown in the reliability report. We would be happy to send you a PDF version of this by email. This is an overview of our FFC types. Let me explain how such a cable is made. The central point are the copper tracks. You can see it here, which are applied to a foil. These are joined to the insulation here. The contact surface and the support tape with a hot melt adhesive. This process takes place with a temperature and pressure. You can see it here. So the so-called support tape is always on the opposite side of the contact surface. At FPC, this support tape is also called stiffener. This serves to ensure mechanical stability, and this enables the cable flexible circuit board to be inserted more easily into the connector. The difference between type 1 and type 2, this is type 1, and this shows you type 2, are that type 1 has the contacts on the same side, and type 2 has them on the opposite side. Here it's on the same side, and here it's on the opposite side. We have different cable lengths. These are 50, 100, 152, and 200 millimeter. Let me show the customer-specific service in detail on the following page. So how can we now integrate the cable into the application? Typical applications for these cables are display and keyboard connections, board-to-board connections, test and measurement systems, industrial applications, and consumer electronics. Ultimately, FFCs are used wherever a robust and flexible cable with a small dimension is required for data transmission. At the beginning, we talked about different standard cable lengths. These were 50, 100, 152, and 200 millimeter. If you can't get along with these cable lengths, you often only have a special length with a corresponding MOQ or a new solution. In order to close this gap, we have decided to produce folded FFC cables. We also produce them in different lengths, 3 in number. However, this length is much more flexible. Variant 1 from 120 to 200 millimeters, variant 2 from 165 to 350 millimeters, and the variant 3 from 280 to 500 millimeters. The folded FFC are also available as type 1, so the same side contacts, and type 2 opposite side contacts. Our new foldable FFC has the same specification as the existing FFC, but can be pulled out to different lengths. Here we see an overview of the available versions. The version on the right, this one, our longest variant, has 2 series of folds. You can see it here and here. This is only for the mechanical stability of the cable. Another highlight is that the different lengths overlap. There should be, so you can see it here, it goes from until 200 millimeters, and this one begins at 165 millimeters and so on. So there should really be the right cable for every application. The folds are made in an automatic process in a machine. We would also be happy to manufacture customer-specific FFCs for you. The MOQ is 5,000 pieces. The requirements here can be very different. There are new polarities, there are different lengths, folded cables, you can see it on the left, gold-plated FFCs, and shielded cables. Please speak to our sales staff about this. They will be happy to help you further. From here, we start with the electrical characteristic of our system. In particular, we describe the impedance in the following slides. Basically, one can say that the reflection phenomenon does not behave linearly. The representation shown in the figure quantifies the signal which is transmitted as well as reflected. These curves are, however, the theoretical curves. Detailed measurement results will follow. However, it can already be seen here that our system is balanced with an impedance of 50 ohms. With this impedance, we have almost no reflections. You can see it here. And a signal of almost 100%. The more the impedance varies, the more important the reflection becomes. This is why impedance matching is so important. After all, we want to transmit the maximum of the signal. Based on the theoretical values just displayed, we have produced various test setups in the laboratory as shown above. Basically, our test setup consists two ZIF connectors. You can see it here and here. One FFC cable in the middle and two SMA connectors on the right and on the left side. These SMA connectors are only for better connection options to our network analyzer. SMA connectors and connecting cables to the analyzer were calibrated before the measurement in order to determine the characteristic impedance. We have chosen two measurement methods. It's on the left side the unbalanced measurement or the single mode. Here you can see one ground connection and one signal connection. And on the right side, the balanced measurement or the differential mode, this one signal and two ground connections. In this way, behavior can be achieved that becomes close to coaxial transmission on this side. The measurement results shows a typical curve using the TDR, time domain reflectomy configuration using a 200 millimeter long FFC cable with a pitch of 1.0 millimeter with a rise time setup of 32 picoseconds to increase the measurement accuracy. The equivalent frequency here would be 6.88 gigahertz. We can see, or what we can see is that in the area of the cable, it's the section 3 here. The impedance already increases to 130 ohms in single mode. This both in the 0.5 millimeter grid as well as in the 1.0 millimeter grid. We remember the target impedance of 50 ohms to get minimum reflection. This looks much better in differential mode with 85 ohms. You can see it here in the table. In zone 2 and 4, here and here, the impedance is unstable. Reasons for this are SMA junctions and ZIF connectors that cause noise and make the measurement unstable. The protective film of the measured cable consisting of PET or different of different thickness and colors, therefore different impedance. As already mentioned, our main focus is on the frequency characteristic, since many applications require little loss to be considered across the entire frequency spectrum, not just a specific range. In this representation, we can see the differences between the single and the differential modes very well. At a frequency of up to 3 gigahertz here, we only have a loss of about 5 dB in differential mode with an almost linear progression, this line. In single mode, it looks much worse. There are big breakouts in the range of 250 here to 1000 megahertz here. From a frequency of 2800 megahertz, it's about here, we have almost completely lost our signal. The losses have been quantified up to a frequency of 3 gigahertz because this should cover most used cases. Let's look at the influence of cable lengths. The diagram shows our different lengths of a 0.5 millimeter FFC in differential mode. These are the different cable lengths. We can see that the trace and the losses are relatively similar, and the cable length has only minimum influence of the signal or the losses here. At a frequency of 3 gigahertz, we see a difference of about 2 dB here on this side. It looks a little different with a grid of 1.0 millimeter. The curves are still relatively similar, but here the losses become significant larger with increasing frequency and longer cables here. This should definitely be considered when designing. Our conclusion, we have described here a practical method to determine the impedance of an FFC. Impedance was measured in a balanced mode as well as an unbalanced mode. The balanced mode is recommended for greater system stability and to avoid unnecessary losses. The measurements were taken by TDR, time domain reflectometry, and with the network analyzer. In TDR mode, the FFC impedance is only measured for a defined frequency. This setup has shown that cable length has no effect on impedance. Network analyzer covers the full frequency range at the same time comparable with customer applications. It's PCB, transitions, connectors, and cables. More typical is the measurement of the impedance value, which contains relevant information. Results underline that below 2 gigahertz, regardless of the constellation, the signal losses are around 4 dB, which is good. When bending the FFC, no changes or additional losses could be determined. In our trilogy of connectors, we have devoted a whole chapter to the subject of impedance at FFC. Please use this opportunity for more detailed information on this topic.
This podcast was taken from a Wurth Electronic webinar. To view the materials and replay the webinar on demand, visit our website at www.we-online.com/webinars or click the link attached in this podcast. You can learn more about our connectors division and find our complete connectors portfolio by visiting Wurth Electronic online. Look for this episode in our profile or click the link available in the podcast. You're listening to Wurth Electronics What's Up radio podcast, and each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Wurth Electronic technical specialists who will shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Wurth Electronics What's Up podcast.